Good morning. We are moving along with Chapter 4 today. Last class we had looked at Chapter 4, we had introduced Chapter 4, and we said that this was really getting into the central portions of the course. So I want to go back and look at a few review items here. First thing, we talked about the laws of motion. We said the first law says if there's no forces acting on something, that objects will, if they're at rest, they'll stay at rest. If they're in constant velocity, they'll continue at constant velocity in the absence of forces. So it takes a force to change the velocity of an object. If an object's moving at some velocity and there's no forces slowing it down or speeding it up, then it will just keep moving at that same speed. Now there was a second law that said when there are forces present, those forces can result in an acceleration. Now, whether or not there's an acceleration depends on, when I look at all the forces combined, do they all cancel out? Forces can oppose each other, and so if all the forces cancel out, then if there's no net force, then the acceleration is still zero. But if we have some kind of a leftover force, when we look at all the forces, if we find that there is a net force, then there will be an acceleration. And here what we're showing is that that's going to be true in all three dimensions. Now we've only got two here. 99% of the examples we look at are two-dimensional, but from time to time we're going to have to be prepared to do a full-blown three-dimensional analysis of forces. And that involves looking at all the forces along an x direction and a y direction. Now we get to decide how the coordinate system is set up. So the same thing we saw back in kinematics. When we look at a situation, to analyze it, we want to be able to look at a situation and ask, what would be the best coordinate system to work from that would make this problem either the easiest to solve, or the one that's most clear about how all the concepts are working. And usually those are the same thing. So anyway, we'll continue to look at how do we set up a coordinate system in a given situation. So we've looked at some examples of this, but let me just again refer to these formulas, and then we'll come back and pick up kind of where we left off. So the first and second law both are included in these formulas. And it says that we look in the x direction, add all the forces together, divide through by the mass of the object. So the more mass an object has, the more stuff it's made out of, the lower the acceleration will be for a given force. So, and that makes sense, right? If you're pushing something with a lot of mass, you're not going to get as much of a response in terms of its acceleration as if it has a lower mass. And then x and y directions, we treat those independently. Forces in the y direction specifically are what are going to determine what the acceleration will be in the y direction. So the directions match up. Here's an example of one of those diagrams. Again, I'm going back and doing a bit of a review here. But there's a couple possibilities going on here. I've got an object, maybe it's this textbook sitting on this table here. And what's happening is there's a gravitational force. We've learned that gravitational forces are going to be represented by mg. Now, that's also kind of an interesting feature or property of what's going on here. Mass has two distinct properties. Mass shows up in this formula, the first and second law combined. And in this formula, mass is an inertia that says that it helps determine how much acceleration there will be for a given force. But the mass that we have here is a gravitational effect specifically. So this mass refers to any kind of a force, whatever forces I'm exerting on an object. I take all those forces, combine them, divide through by the inertial effect of the object to determine what the acceleration is. So, one example that we talked about, or we kind of suggested, was just accelerating an object. So here I'm accelerating this book, I'm changing its velocity, and I can feel that it's got a certain heft to it, right? Now that's different from just lifting it. So lifting it, I can feel that I have to oppose this gravitational force, this mg. But any kind of acceleration, I could have it sitting on this table and sliding back and forth, and the force that I push with, in determining how much acceleration we'll get, we would have to consider the inertial property of the book. Okay, so property number 1, inertial mass. Property number 2, gravitational mass. And I'll try and continue to point those things out as we go through. That's an important concept to keep in mind. So with this object, and again, it's a bit of a review here, but it's really, this is the basic stuff. This is the stuff that we're really going to be focused on for the next several chapters. And again, it's something we're going to actually be working from for the rest of this course and beyond. So gravitational force, I'm applying that in my diagram. I'm kind of putting that at the center of the object, what we consider to be the center of mass. And then there's a normal force. There's a contact force here in this particular example, and that's a force acting on the book or on this block that we have here. So we're isolating one object. In this case, it's this block or this whatever object this happens to be. And the normal force is pushing up on it. Gravitation is pulling down on it. Now, I can push on it. So the idea here is I could exert a force and push. Now there is friction on this surface. It's much more common to have friction than not. And so here is the friction force here while I'm pushing. Now what the first and second law tell us then is, all right, here's this object. It is moving in some direction. I'm pushing on it. What will its acceleration be? And there's two possibilities. One possibility is that the F net is 0. And by F net 0, we mean that I'm pushing just enough to offset the frictional forces. So if I push just enough to offset friction, then if there's 20 newtons of force in this direction and 20 newtons of force in the other direction, those forces will cancel out. That gives me an F net in the x direction. Now in the y direction, we've got kind of the same thing going on here. The normal force is in the positive y direction. Gravitation right now is in the negative y direction. There is no acceleration taking place. That tells us that the F net in that direction has to be 0. So we had written down these two possible categories of motion. Either, well, I guess the motion is on this side. Either it's in constant velocity, or the velocity is somehow changing. It's one or the other. And constant velocity, we've been saying over a few times, is very restrictive. Constant velocity requires that you're maintaining exactly the same speed in the same direction. It's got to be a straight line. Okay. Now we also pointed out that at rest is a subcategory of constant velocity. If something's at rest, and not just at rest, but continuing to stay at rest, then that velocity is remaining constantly 0. All right. So the other possible category that we would have, constant velocity versus changing velocity. Well, changing velocity means there is an acceleration taking place, and that tells us that the forces are not balancing out. They're not canceling out perfectly. If an object is undergoing an acceleration, it must be that there is some net force, some leftover force, when we look at all the forces combined. Now this is a nice example to come back to too, because it's got 2 dimensions, and so we can go through and analyze how these forces are related in terms of their magnitude. So it's either no net force, or yes, we do have a net force. If there's no net force, there is no acceleration, the velocity will remain constant. Those 3 things are just 3 different ways of, well, they all go together. So if there's no net force, there will be no acceleration. If I see something in constant velocity, that tells me there is no net force. So we can start either way on this. And this is a good example because I can see from the book, on the table, that there is no acceleration taking place in the y direction. And so I can start by saying, oh, there is no acceleration in the y. In fact, it's at rest. So there can't be any net force, and that tells me that whatever mg is, if this is 40 newtons, then that's got to be 40 newtons also. Okay, so we can use these reasoning back and forth, and that's it. That's kind of the diagram to work from in all of these examples. Okay, and we did look at some examples, and we'll look at some more examples. Let's get to where we were. We had introduced a third law. So I don't know, 3 is the magic number, I guess. So the first and second law were included in that formula that we just took a look at. But the third law has a little different feel to it. The third law says this. It says that any time a force is exerted on an object, that force is caused by another object. Whenever one object exerts a force on a second object, the second exerts an equal force on the front. I kind of like this. I like this statement that the textbook slides have. Sometimes the third law gets presented as for every action there's an equal and opposite reaction. And by action they mean force. And it's not that you push on something and there's a time delay and things start pushing back. So it's not that you go up and you push on a book and then the book goes, it wakes up and it goes, oh, maybe I should push back. Once that contact is made, the force is already present in both directions. So when two objects come into contact, so the third law works really, really well for contact forces. And what we had pointed out in the last, kind of at the end of the last lecture, is that when we look at gravitational, electric, and magnetic forces that act at long distances, these forces are not instantaneous in both directions. So, for example, I think we used the example of the Earth and the Sun. If the Sun suddenly disappeared, Earth would continue to feel the gravitational effects for about 8 minutes. It's kind of an interesting effect that its influence, the influence of an object with mass, spreads out from the object. Now, it's not like there's anything moving, nothing physical moving, but this influence, this field, this gravitational field, spreads out or propagates. Now, it works in both directions, so if we're thinking of the third law, we could go, well, if the Earth feels the Sun's influence from 8 minutes ago, what about the Sun feeling the gravitational pull of the Earth? Because there's certainly a gravitational effect in both directions here, and it works both ways. So the Sun is currently experiencing the gravitational field of the Earth that was generated or created 8 minutes ago. So there's a time delay in both directions. So we said that's a little, that adds this complication, but it turns out, in practical terms, it doesn't really affect the way we set up and solve problems, unless we're specifically looking at this delay effect, because the Sun is still there, we hope, and the Earth will continue to be here too, we hope. And so it turns out not to be so important. So for our purposes, when we set up these diagrams with forces, these free body diagrams, we are going to make use of the third law. So we're going to say, certainly over short distances, we can treat them as perfectly, as instantaneous. Things happening very, very rapidly with gravitational, electric or magnetic forces. All right, so here is a person's hand pushing on a table. As soon as contact is made, there's an equal force in both directions. It's kind of like when my kids were small, I think of the third law. And one of them would say, he came up and shoved me. And I would say, well, let's think about this. There was a force in both directions, right? And it must have been that it was simultaneous. When your brother pushed you, you pushed your brother at the same time. So, what should I do about that? And they go, yeah, but he pushed me harder. And I go, no, actually the magnitudes were the same. So, if you pushed your brother with 50 newtons of force, then he must have been pushing back with 50 newtons. So there's not a way to sneak up an object and push on it, with a contact force, without immediately setting up forces in both directions. Those forces will be acting on two different objects. Notice that when we do the force diagrams here, one of these pairs of forces, one of these interaction force pairs, one of the forces is acting on the hand, the other force is acting on the table. So when we isolate the two objects, these two forces aren't going to cancel out. Okay, so sometimes it feels like if they're equal and opposite magnitude, shouldn't they cancel out? Well, they won't if we're isolating these as two independent objects. So let's move on from this. Okay, so here's another example. Here is a skater out on the ice and holding on to the wall right now. And so this skater comes up and I guess skates into the wall and puts out her hands to hold herself there. And so there's a force on the wall when the skater comes up, and then the wall is exerting a force on the skater. And this is just emphasizing the fact that these are two distinct objects, so I've highlighted those. There's the wall is experiencing a force, and the skater is experiencing a force. The magnitudes are the same. The forces are in exactly opposite directions. But when we do a force diagram on the skater's going to have gravitational force, going to have normal force, going to have this force, but this one's not going to show up on the skater's force diagram. So that effect of the wall, force coming from the wall onto the skater, is going to slow the skater down and create a deceleration. All right. Here's another example of the third law of motion. Rocket propulsion. So here's the space shuttle launching, and how does this work? There's clearly a force acting on the space shuttle configuration here. So we've got a force, and it's coming from the rockets. I mean, this is a little bit of rocket science here. How does that work? And what happens is we generate these very violent chemical reactions inside a combustion chamber. And so that says that the gas molecules, or the molecules of the products from this chemical reaction, push against, here's the combustion chamber inside the rocket. The gas molecules are bouncing around. They push on the combustion chamber, and then they exit from the other side. So that says that if they're exiting from the other side, probably the last contact force they made with the rocket, again, these gas molecules, was pushing against the structures within the rocket. So there was a force that happened. The rocket pushed down on the gas molecules pushed up, and the third law of prediction is these two objects are pushing against each other, and they're going to separate. So the fuel used to be at rest inside this rocket, but when the fuel pushes against the rocket and the rocket pushes against the fuel, they push each other in opposite directions. So I thought it was interesting here that it said that the rocket doesn't need anything to push against. It actually does. Now, the rocket's not pushing against the air. The rocket's pushing against the exhaust, the products from the chemical reaction in place, the combustion chamber. So that's where the push is taking place. So one more time, the gas molecules inside here are pushing on the rocket upwards, the rocket pushes down on the gas molecules, and the two objects separate as a result of those forces acting between them. So if we are in a car, what is it that makes the car move forward? What forces are used to accelerate a car what forces are used to decelerate a car? And that's kind of an interesting question. I mean, we have these force diagrams that we've drawn for these cars, but where is the object? How should we isolate the car? It says here that the common answer is that the engine is what's making the wheels go around. But if we're on slick ice, so if we're on very smooth ice with very, very little friction, the wheels just spin, for example. So friction is what we're really depending on. If there's not friction between the tires, the place where the contact point, where the tires are in contact with the pavement, if there is no friction there, then we can't speed the car up, we can't slow it down. If the car's already moving, we put the brakes on, that doesn't slow the car down. So we really depend on that friction force, unless, I mean, there's other things you could do. You could attach a big sail on top of your car, and you could use the force of the wind to push you forward or slow you down or turn. You could have jet propulsion taking place. You could attach some jet engines to your car and use the forces from the jet engines to push it forward or back or whatever. But when we're driving cars in a standard manner, we're really thinking that we have to think in terms of the friction between the tires and the pavement. Now, this is a third law effect. And so let's actually take a look at it. I want to get a force diagram on this. So here's the car. Now what I did do is I drew in separate normal forces. I was trying to be a little more careful here. So I drew in separate normal forces, and I should have N3 and N4 on the other side of the car. So assuming we have 4 tires making contact with the pavement, now we've got the possibility, now I drew this friction as F, big F. I guess sometimes I'm using little f. Anyway, so here is a force of friction. Now I'm going to say this is it's an all-wheel drive car. So we'll say all 4 wheels are getting a force from this. And so the engine is connected to, you know, a bunch of mechanical stuff which attaches to the wheels, and the engine spinning around, that motion gets transmitted to the axle spinning around, and that's attached to the wheel, and the wheels spin. Now again, if there were a perfectly frictionless surface here, what that would lead to is just wheels spinning. The car wouldn't go anywhere, but the wheels would spin really nicely. Because there is friction, what happens is as the wheels begin to spin, that creates a backwards force on the pavement. The wheel is pushing against the pavement. If you've got good tread on your tires, then the tires will not slip against the pavement. And so when the engine begins to turn the tire, that creates a backwards force. Now, that's not the only force that gets set up. If I've got the tire coming into contact with the pavement, and it's not going to slide, then if there's a force of friction of the tire pushing back on the pavement will create a force in the opposite direction. So that's what we're counting on, is this force from the friction along the pavement to push the tire forward. Now the tire is attached to the rest of the car, and so if we were isolating this object, the car, then I would, draw my isolation box like this, include the entire car, all the occupants, and the tires, right up to where they make contact with the pavement. Now that means that I'm going to include the gravitational force, I'll include these normal forces, and there is the frictional force pushing the car forward. Now what happens when we put on the brakes? Yeah, and so we get the opposite effect happening when we put the brakes on, right? When we put the brakes on, the brakes exert a frictional force on some brake pads, and that prevents the tire from, the wheel from rotating as quickly. It slows that effect down. And now what's happening is the wheel's going down, but the wheel's not going fast enough to keep up with how it's traveling along the pavement. And that creates a force in the opposite direction on the pavement, and the pavement will exert a force backwards. So we depend on friction for everything when we're driving, right? We depend on that for accelerations forward. We depend on it for decelerations. We depend on it for turning, accelerations to the side. So we'll be looking at circular motion here, not this chapter, but chapter 5. And when we look at circular motion, we realize, oh yeah, I'm going to need a force. If I'm driving down the highway and I want to speed up, I need a force in the forward direction. That's going to come from friction. If I'm driving along and I want to slow down, then I put on the brakes. That's connected to the tires in a way where now the pavement is going to be exerting a force backwards on the car. And then if I want to turn left or turn right, I'm going to need a force in that direction, because if I currently don't have any velocity in the sideways direction, I'm going to have to accelerate in that direction. I'm going to have to accelerate sideways. I need a sideways force to do that. And it's all coming from friction when we're driving. So, when you're the DMV and you're taking the driving test, remember when they ask that question, what forces are you using to accelerate or decelerate or turn your car from left to right? Friction, okay, so it's frictional forces that we are using for that. Okay, now another thing to consider here is, how do we walk from one location to another? It's the same thing. So, you put on your shoes, and the shoes have frictional forces, or not shoes, but your feet or your socks or your shoes, whatever. You depend on a frictional force. So when you push back, here I am walking, and I can feel myself, I set my foot down, but then I push back off that foot. If it were a slippery surface, if there were no friction, my foot would just slide out from underneath me. So I depend on frictional forces. I can orient myself in a way where I'm pushing back on the floor. My foot or my shoe, where it's making contact, is pushing back on the floor, and that sets up a third force pair. So the floor will push forward on my shoes, and that propels me in that direction. That allows there to be an acceleration. So that's a very important third force pair, and it's one that you have to stop and think about a bit. It's not the easiest example to think about. So when you're walking, again, I think we had an assignment, right? You guys were supposed to practice going at constant velocity, and then practice accelerations and decelerations. Do that for a few minutes, and think about your foot pushing off the floor and go, oh yeah, that's how it's done. It's depending on these frictional forces acting on the floor. So I guess this is it, right? Yeah. So in this case, here is this person, with their physics textbook, and pushing off right there. That's creating a forward force by pushing against the floor surface. The floor surface is pushing the person forward. So setting up that force pair between, it's like pushing off from anything, right? If I push off from this wall, here's this wall, I push off of it, I'm pushing on the wall is pushing on me. That has an acceleration effect during that time while I'm pushing. Okay, so here is another example of this. So here is Michelangelo's assistant. Anyway, here's a sled with a block of marble, and apparently Michelangelo is going to be carving this. And here is the sled. And what they're asking in the problem is, hey, there's a force pulling the sled forward. There is a force pulling the assistant backwards. Those are a force pair. Now, if those forces are equal in direction, equal in magnitude, but opposite in direction, then don't they cancel each other out? They don't if we're treating these as two separate objects. So I highlighted this. I said one object is the sled with the marble or granite marble on it, and the other object is the person. So if I'm looking at all the forces acting on the person is being pulled back by the sled, but then that boundary comes into play and the other force isn't acting on the assistant. So then it comes down to this. The person's going to have to be able to push back on the floor or the ground enough, there's going to have to be a large enough frictional force that this person can push off the ground forcefully and continue to move forward by pushing himself forward with a force at least large enough to offset this force where he's being pulled back by the force from the sled. Similarly, the sled's going to have frictional forces on it, and so the force acting on the sled, I guess they should really have crossed these out. Maybe I should have put something on this. So this is the force on the sled. The sled's being held backwards by the friction. This is not acting on the sled. This is acting on the ground. So let's get rid of this one. So if this force is acting on the sled and this force is acting on the sled and this force is as large as this one, then the sled can continue moving forward at constant velocity. Similarly, this person is going, here's the force of the ground acting on the person, not this force. This one's acting on the ground. So this force is acting on the ground, and this force was acting on the ground. Okay. So those aren't in the force diagram for those objects. Okay, now what we've been drawing, these force diagrams, are officially referred to as free body diagrams. I probably will call them force diagrams more often than free body, but the free body idea is that you isolate things. So here is the sled, and there's a gravitational force. I listed its mass as m1. There's a gravitational force, m1 times g. There's a normal force acting on the sled, and since there's no acceleration taking place in the vertical direction, it certainly looks like those two forces are the same magnitude. The normal force, if this is going to be a lot of newtons, right? If this is 20,000 newtons, 20,000 newtons, then this has got to be 20,000 newtons also, because I can see that there's no acceleration taking place in the vertical direction. So vertical forces are canceling. Now what's going on in the horizontal direction? At least to get this sled started, we had to exert a large enough force to create just enough of an acceleration to get it moving. Once it is moving, then the tension of this cable, the tension in the rope, would have to match the frictional force acting on the sled. So here's the sled, and if the tension is bigger than the frictional force, then there's going to be a forward acceleration and the sled will pick up speed in that direction. If the tension matches the frictional force, friction 1, then the acceleration will go to 0. Now remember, acceleration going to 0 doesn't mean it stops. Acceleration going to 0 means it continues with constant velocity. And then finally here, if the tension drops off, then it will slow down. The frictional force is now larger than the tension, then the sled slows down. So to get the sled started, there needs to be a tension larger than F1. To keep it moving at constant velocity, they need to match, and then when we're ready to let the sled slow down or take a break or something, the tension could drop back down, friction could slow it down. Now here is the assistant over here, and what we have here is a frictional force from the person, from their shoe, pushing against the ground, I guess, is what's going on here. So here, it looks like a block, right? So this is object number 2, and that's the assistant, and hey, we just get to treat objects as blocks in these diagrams if we want to. So here is the assistant, here is the force of the ground pushing the assistant forward when the person is pushing back with their shoe. Here's the gravitational force, here's the normal force. These appear to be the same because there is no acceleration vertically. Now there could be an acceleration taking place horizontally. And that is going to depend on is the force of the person pushing back on the ground is going to match the force of the ground pushing on the person. If this force is bigger than the tension, because there's a tension pulling back on the person's holding onto that rope to pull the sled along. Same deal. So if F2 is greater than t, then there will be an acceleration. If they match, then there will be an acceleration forward, I should say, on this first one. And then this would be constant velocity, and then this would be slowing down. So now, there's a little flexibility here as to how to draw the force diagrams. We have drawn these as two independent objects. We could treat them as one object. So here we are going back, and if we wanted to, in a particular problem, we could draw our isolation box around both objects together and say, let's just treat it as one object instead of two distinct objects. If we do that, then we don't have to consider the tension anymore. So if we draw the box big enough to include both objects, then we ignore what we call internal forces. Forces that are acting between objects within the system that we've defined, and they do go away if that's the case. So again, if we're treating them independently, then these are going to show up in our force diagram. If this is just one object, then these would drop out of the force diagram. These are not here at all. And the only forces left would be the force of the ground pushing the person's foot forward and the frictional force from the sled in the opposite direction. And it would come down to those two forces. Okay. Now, why might we want to treat these as one object? And you go, well, I think the assistant and the block are going to have the same acceleration at all times. They're going to be traveling at the same speed. If one speeds up, the other one's going to speed up. If one slows down, the other one's going to slow down. They have the same motion. We could treat them as one object. So that would work. We can go back and forth in a particular problem. And we can go back and forth and treat them as separate objects or as combined objects. We're able to do that, okay, in order to solve a problem for whatever we're looking at. All right, let's talk a little bit about weight. Now, as I've mentioned, I'm going to avoid using the word weight. The word weight to me is a little bit dangerous. It tends to take on different meanings under different circumstances. So, and I'll try to point to those examples as they come up. So for me right now, I'm just going to call the force of gravity the force of gravity. And the force of gravity, as we've already pointed out, is given by m times g. Now there's some vector signs here that say whatever direction little g is in. Now little g is referred to as the gravitational field. So I'm going to start calling it that. I think here, yeah, so I'm going to start calling this little g the gravitational field, and I'm actually going to start using different units. When we're looking at force diagrams, rather than using meters per second squared, I'm going to tend to use newtons per kilogram. And that reminds me that little g really is going to help me keep track of the gravitational forces. I can take this gravitational field, little g, 9.80 newtons per kilogram, and multiply by the mass. When I multiply by a mass, the kilograms will cancel out, and it's going to, mg is going to have units of newtons. Okay. So force of gravity, again, I should be crossing out weight here, huh? So on that title, I'm crossing out weight. I'm just calling it the force of gravity. Now, they're comparing the force of gravity and the normal force. In the examples we've looked at so far, with something sitting on a table, on a level table, the normal contact force is going to be vertical. The gravitational force will be vertical also. So in many cases, but certainly not all, the normal force and the gravitational force will be acting on objects in opposite directions. So if I have something just sitting on a level surface, remember at rest is constant velocity, often we find that the force of gravity matches the normal force. So N equals mg for a simple diagram like this, if there is no acceleration in the vertical direction. Okay. Now what they're pointing out here is that if we place heavier and heavier objects on the table has a little bit of elasticity to it, and that's where the normal force comes from. So it's kind of like putting it onto some springy material, and the material begins to push back. You know, when I set this book, and the book's pretty heavy, it's got a fair amount of mass here, and so the gravitational force, mg, is acting on it, and you know, gravity's acting on it here, but the table isn't at this point. When I set it onto the table bends a little bit. Now, it can often be such a small effect, we don't pick it up. But if you take a really heavy object and place on this table, you would start to see that the table is bending a little bit. And so we're depending on elastic forces within the material itself to push back on these objects when we set them down. And that is what is the source of this normal contact force when we set objects on surfaces. Okay, here are the two properties of mass. I just want to remind us, we've now looked at the official slides for the gravitational force. The gravitational force is F is equal to mg. What does that look like? Well, if I have an object and it's got mass m, then there will, and it's in the vicinity of a planet or a star or something, and you know, as you know, 95% of the examples we look at, we're going to be looking at the gravitational field of the Earth near the surface. We kind of spend our lives, for the most part, living, for most of us, our entire lives, within a very narrow range of elevations along the surface of this planet. And so in that region, the gravitational force will be mg, where g is going to have this value of, the gravitational field is 9.80 newtons per kilogram. Now, the inertial property of mass is in this equation. So here, again, it doesn't matter what forces we've got. In this case, there is some forward force acting on this object. We're ignoring the others. There's going to be an acceleration that takes place, and if the object has more mass, then the acceleration will be lower. Okay, so it's still kind of a mystery as to exactly why these two masses are identical, but it did provide kind of the starting point for Albert Einstein to develop the general theory of relativity. So this has been something that physicists have wondered about for hundreds of years, and anyway, we'll move on from that. So, and I'll try and point out those two properties. Ooh, there's a lot of stuff going on here. Let's see. So, what it's saying we're doing here, we're setting an object on a surface, and so what we've got is we've got that normal force, we've got this gravitational force. The combined effect has to be 0. How do we know that? How do we know that F, the normal force and the gravitational force for this first example, they've got to match? And that's because that box is not undergoing a vertical acceleration. We're specifically looking at the y direction. There is no acceleration happening here. In fact, not only is the velocity constant, the velocity is constantly 0. The object's at rest, at least in the vertical direction. And so the normal force and the gravitational force have to be equal in magnitude. Now, they're not a force pair. This is not the third law at work. These are two different forces that are acting on this object. And they happen to be balancing at the time. Now, in the second picture, a person walks up, pushes down on that object. So pushing down on the book, what effect is that going to have on the gravitational force on the book and on the normal contact between the book and the table. So the gravity is unaffected by this, right? The book still has the same amount of mass. You walk up, you push down on the book. Well, gravity's still pulling on the book with the same amount of force. But now the normal force is going to have to be larger. If I push down on the book and the table doesn't collapse, I'm not pushing that much, then it must be that the book now has an additional contact force. See now, there's a contact force coming from above, pushing down on the book. And this diagram is saying that that happens to be 40 newtons. So if somebody's pushing down with 40 newtons here, well, the upward contact force, there's a contact force at the lower edge of the book coming from the table, that's going to have to push up enough to offset the gravitational force and to offset this additional 40 newtons. If the table's not capable of doing that, the table will collapse. Okay, but the table looks sturdy enough, an additional 40 newtons is not going to cause a problem for this table we have here. But it could if the force got really large. Now the other thing they're going to try here is, instead of pushing down more, now they're going to attach a cable and they're going to pull up on the box. Not so much that it lifts it off the table. It doesn't completely, this is not as large as the force mg, but it's going to reduce the normal force at the bottom, because now the book it continues to have one downward force. So in that last picture, the only downward force is mg. But there are now two upward forces which combined will add up to mg. So whatever mg is, maybe mg is 100 newtons. So let's say that mg is 100 newtons. We have now, with this tension, we're supporting 40 newtons of that. The normal force is going to have to pick up the additional 60 newtons in that case. Okay, so if we went back and put numbers in, we could say the gravitational force here is 100, normal force has to be 100. Here the gravitational force is 100, plus there's an additional 40 newtons pushing down on the top. The normal force from the bottom is going to have to be 140. And then here, if the tension is providing 40 newtons, then the normal force at the bottom doesn't have to provide as much. In that last picture, what happens if the gravitational force is 100, but the tension becomes 100? Well, if the tension becomes 100 or more than 100, then the box will lift off the table and begin to accelerate upwards. Okay, and yeah, I've got diagrams for this. So here's the picture. I should have just used 100 newtons. Anyway, I went with 10 kilograms, so this worked out to be not quite 100, but 98 newtons. Now, as long as I can observe that there's no acceleration in the y direction, that tells me that adding all the forces together in the y direction, exclusively the y direction forces, are going to have to add up to be 0. So in that first example, adding all the forces together in the y, those were n minus mg. They have to add up to be 0 because the acceleration is 0. That means n is equal to mg. Normal force would have to be 98. In that second example, we now have, well, everything we talked about before, an additional 40 newtons pushing down. That requires the normal force from the table to go up by 40 newtons. That puts us at 138. And then finally, that third example, we are using the tension and the normal force combined. The forces in the positive y direction have to balance out with the downwards. And again, the reason why is we're assuming that no acceleration takes place. We're observing the box, it did not accelerate. Therefore, no acceleration tells us that the sum of the forces in the y direction, that's got to add up to be 0. Now, when I carry out the numbers on this, it works out to be 58 newtons. So, these are good examples to look at. Practice these examples. Check your reasoning at each step. So what happens in these kind of examples
is it's easy to get a sign reversed. So I put all the forces here that are upwards on one side, and then I put all the forces downwards on the other side. So I'm setting this up so that each one of these terms independently is a positive number. I'm not going to say that mg is a negative value. Mg is a positive value, but its direction is negative. So I'm keeping track of that by putting it on the opposite side of the equation. Okay, that's what it looks like. And then from there, I can start doing the algebra. I can carry the t over to the other side and solve for. I can isolate n and solve for it. All right, here is, we are going to accelerate. Oh, here we go. All right, so everything we talked about, here is 100 newtons here. We're finally going to pull and create a tension force acting on this box. It actually just looks like an envelope now. But it's a box. It's a big heavy box, 98 newtons, not too heavy. But we're going to pull up with 100, so what would that be? That's like 20, 25 pounds of force. So this object, if we weighed it, I wasn't going to use the word weight, that mg is going to be about the equivalent of 25 pounds or something. So I'm pulling up with a little extra, 25.5 pounds, something like that. That's going to create an acceleration, but it's going to be pretty modest. And here's the reason why. Let's take a look and see. So I have a tension force upwards. I have an mg downwards, and it is the case now. We're saying that the tension has become larger than mg. So what I can do is I can come in and I can look and calculate how large is the gravitational force. Well, the gravitational force on a 10 kilogram object would be 98 newtons. The tension is at 100 newtons. So I'm getting a net force, but it's not very impressive. The net force is going to be 2 newtons, and it's going to be in the upward direction. So I've got this net force of just 2 newtons upwards. Well, how much acceleration is that going to create? Well, the formulas that we said we start from is acceleration equals sum of the forces divided by mass. So here are the forces: tension minus mg, that's the net force acting on the object. But then I have to divide through by m. Now here's an example, maybe our first example of saying, m is playing 2 different roles here. What kind of a mass are we thinking, and what property of mass are we using here, and here, and here? And this is what we call the gravitational property of mass. The mass will determine how large the gravitational force is. The mass in the denominator here, that's the inertial effect. Once we've determined how much force we have, then we divide by the mass to create that inertial effect. And we don't have a very large force, net force. The net force is only 2 newtons, and the mass is 10 kilograms. And so when we carry out that calculation, the acceleration that we get in the y direction, specifically the y, everything here is in the y direction, 0.20 meters per second, and it's going to be in the upward direction. The acceleration will be in the same direction as the net force, okay, always. So that's what this is going to look like. So now here is another example with the force of gravity. So here's a person in an elevator. The elevator can be moving at constant velocity. The elevator can be accelerating downwards. The elevator can be accelerating upwards. So we've got a number of different possibilities here. How will the normal force compare with the gravitational force as these accelerations take place? And the first thing we want to point out here is the person's mass is not changing. The gravitational force will not be changing. So it says the person is 65 kilograms, and it says that currently the person starts at a high floor in the building, and then initially at first they accelerate downwards. they pick up a little bit of speed because the elevator started at rest, right? And if we don't accelerate a bit, we'll just stay right there. And so they pick up speed a little bit and then probably go constant velocity. So during that short period of time when they're picking up speed downwards, there is a downward acceleration. It says that the downward acceleration is a tiny fraction of the gravitational acceleration. So we're going to have to calculate that too. Person is standing on a scale that is able to read instantaneously. It doesn't vibrate back and forth like real life bathroom scales would. So the person is standing on the scale, and we're going to find out, or we're going to calculate what the normal force would be. What is the scale? Okay, so first of all, there's an acceleration, and then there is and then the elevator goes into constant velocity. So let's calculate both of these. So here is the force diagram. Oh, look, that looks like a person. So here's a person. Here's the gravitational force. Here is the normal force. It's really coming from the floor. But there's a normal force upwards and an mg here. We are told that the person is moving downwards and the elevator, but the person specifically, the object we're isolating here is not the elevator, it's the person. So we're specifically looking at the person and the specific forces acting just on the person. So we've got this gravitational force and a normal force. The normal force is coming from the scales. Scales don't measure mg, scales measure n. So the contact force with the scale is what's getting measured. Now, when there was no acceleration, n equaled mg, so reading the scale would give us a value for the gravitational force. But now let's take a look here. The person's 65 kilograms. The gravitational field of Earth, 9.80 newtons per kilogram. When we multiply those together, the kilograms cancel out. Mg turns out to be 637 newtons. And that's going to stay the same throughout the problem. So I can use that 637 newtons for the gravitational force. Now, they told us that the acceleration that this person is undergoing is 0.2 g. So we can put those numbers in. Oh, why didn't they just tell us? The acceleration is 1.96 meters per second, and the acceleration is downwards. So what we can do is this. I am going to call the downwards direction positive. And that's fine. We saw this back in chapters 2 and 3 when we were looking at determining what direction we wanted to find the coordinate systems to be in. So by defining downwards to be positive, that allows me to use A as a positive number. And that means that the mg force is in the positive direction. So I can use the 637 newtons. Now, what I've got to do is I've got to subtract off the normal force because n is in the opposite direction. So again, rather than calculate n to be a negative value, what we want to do is have n come out to be a positive value. And to do that, we'll put the minus sign in by hand. So I'm saying mg, all the forces in the direction of acceleration, minus all the forces opposing the acceleration, and the normal force is opposing the acceleration of the person. So the acceleration here will be mg in the direction of acceleration minus n, opposite, and then divide through by the inertia. Now, a little algebra on this tells us that the normal force, which is what the scale is going to be reading, is mg minus ma. And we can calculate that number. So here is the mg value. Here is the acceleration. So the normal force doesn't need to be quite as large. The normal force does not need to be as large as mg because there's an acceleration in the direction of the gravitational field. So the normal force will be reduced from what it was. And we can calculate by how much by taking m times a and subtracting that off. Now the m times a works out to be 127 newtons. The person feels 127 newtons lighter. And you know, that feeling that you're not quite as heavy comes from the contact force with the floor of the elevator. You're not feeling like you're in as close contact. The difference here leaves us with 510 newtons of force for the normal force. So what we could do now is, we tend not to think in terms of newtons. Those aren't quite as familiar as kilograms. So they said that the person was 65 kilograms. What does the person feel like when they're standing? And the normal force is equivalent to, it's as if the person were 52 kilograms. Now that's a motion effect. It's because there's an acceleration taking place. The normal force is not equal to mg. The normal force is not 637 because the acceleration is taking place. The person feels a little lighter. They feel like they have 52 kilograms of gravitational force acting on, or that's what the scale would read. Okay, if the scale is capable of reading reliably during an acceleration, and the scale's not bouncing back and forth between different values, so the person would feel lighter. What would happen if the acceleration got larger? What if the acceleration were really large? What possibly could happen to the normal force? And as the acceleration gets larger and larger, the normal force is less and less. We just don't need as much normal force. And kind of in the limit of that, what would happen if we just cut the cable and the elevator just drops at 9.80 meters per second squared? What if the elevator just goes into free fall? Well, if the elevator goes into free fall, then the person inside is also in free fall within the elevator, and the normal force goes away. The person doesn't necessarily stay in contact with the floor of the elevator because of the acceleration that's taking place. Now, if the acceleration were in the opposite direction, person would feel heavier. Now, in part B in the problem, they said, what happens now when the elevator settles in at a constant velocity? Well, the elevator is still moving, it hasn't stopped, but the velocity is now constant. So the acceleration is 0. Now again, acceleration 0 does not mean the elevator stopped. It means there's a constant velocity. The velocity is not changing. So as long as the velocity remains constant, doesn't matter if you're on your way down, if you're on your way up, if you're at rest, anytime the velocity is constant, the acceleration is 0, there is no net force, and n will go back to being mg. It'll go back to being 637. The scales will read 65 kilograms for those times. So it's only during the acceleration when the forces don't balance out. Okay, so we have introduced this idea of free body diagrams, force diagrams, and here's some good advice. Draw a sketch, draw a diagram of what's going on. The example they have here, and I think we're going to come back to this, but let's go ahead and take a look. Here is a boat, and it's being pulled along a canal or something. The boat's being pulled along this waterway, and there's a couple of people on the sides here pulling on these ropes. One is pulling at an angle of 45, one is pulling at an angle of 37 degrees relative to the forward direction from the boat. So we've got this force diagram set up. So draw a diagram, draw a sketch, draw a free body diagram. So you can draw more than one, right? So you don't have to just draw one sketch or one diagram. So here's a picture of what's going on. And then here, notice they've dropped all the people are gone, the boat's gone. These are all the forces specifically on the boat. So for one object, isolate one particular object or one particular group of objects, but be clear about what you've isolated. In this case, we're going to isolate the boat, and the reason for isolating the boat is they want us to answer questions about these forces. We know how large the forces are, we know what angles they're at, and so we're specifically going to be adding together these forces acting on the boat. Now, it's not a complete free body diagram because there's other forces acting on the boat. The boat's got a gravitational force acting on it. The gravitational force is going into the board or into the page. It's downwards. This is a top view, right? This is a view from above, and those are good diagrams. But on views from above, the gravitational force is going into the page or into the board. There's a normal force. The water's pushing up on the boat, and that's coming out of the page. So those forces, and there's certainly going to be a frictional force or water resistance pulling the boat back in this direction. So we've got gravity into the board, we've got a normal force coming out, we've got frictional forces here, and then here are the forces apparently that are pulling the boat down this waterway. So they've chosen just to look at those forces, and then I think what they've done is they've resolved them. So here is the resultant. They've broken these down into components. So I've got an x component and a y component for force A. I've got an x component and a y component for force B. We'll see how to add these together. And then we have to combine them. They've actually shown down here when they combine the forces together, these two forces are not just pulling the boat forward, they're also pulling it to the side. So if the two people continue to pull on the boat at these angles with these forces, there's a possibility that we're going to be pulling the boat off in that direction. But I don't, they're not addressing that, at least yet. So make a sketch, draw a free body diagram, get all the forces acting on there. They've left some out. Resolve the vectors into components. So x and y components on everything, and then use the Newton's law formula for each component, and then solve. So, and that's it. I'm surprised they didn't say, and then look at your answers, go back and check, and see if everything makes sense. So we're going to be taking a look at this in the next class. I think we're through for today. Let me check and just make sure. We'll stop there and we'll pick up at the next class.